Today's lab, I'll be analyzing the motion of the spring with the help of our knowledge of force due to the spring and the energy principle. As you can see, the spring force is defined by the equation -1 times stiffness of the spring, Ks, times the displacement from the equilibrium, x, times the unit vector L hat. We apply the energy principle here. Since this lab involves a spring, we split our potential energy to potential energy due to gravity and spring as seen on the slide. Following that is the derivation of the potential energy due to the spring. Since work is defined as the product of the force and the displacement, we integrate force and displacement and use the initial and final position as the intervals. We substitute Fs with the formula stated above. Integrating that gives us the following equation. Since potential energy is -1 times the work, we get half k delta x squared. Another important formula to keep in mind is the period of the oscillation, which is 2 pi times the square root of mass over stiffness of the spring. As we'll see later in the lab, we are able to model the x position and y position versus time and compare it with our predicted model. Before we discuss the lab in detail, let's talk about why we are interested in analyzing the oscillatory motion. This motion is present in string instruments, electromagnetic waves, alternating currents, and cosmological models, to list a few. As you can see, this motion is essential and hence important to analyze. As the spring oscillates, I added the point masses. It was slightly hard to find the exact center as it tilts a bit, so we could improve it by marking a center on the object before recording. Now that we have our observed data, I went ahead to code a predicted model of the motion of the spring. As you can see, this is a snippet of my code which I used to set my initial conditions. The mass of the ball is given in the instructions, and the ball's position is got from tracker. Since the mass is at rest in the beginning, the initial velocity vector is 0. The period is calculated from the graph, and with the formula I mentioned in the beginning to solve for t, that can be rearranged to solve for k. Using that formula, we get 6.875 newtons per meter for k. L0 is calculated by subtracting L from mass times acceleration due to gravity over stiffness of the spring, which gives us 0.126 meters. L is essentially the ball's position, since spring dot pos is the origin. L hat is simply the unit vector of L. S is the distance of the mass from the equilibrium. Hence, we take the difference of L and L0. Here are the energy formulas. Here's a snippet of my calculation loop. The force of gravity and the force due to the spring have been set to their corresponding vectors. F net is the sum of the two forces. Here are the velocity and position update formulas. And this updates our L and S since the ball's position changes. This updates our energy formulas since the ball's position and velocity changes. Delta K, UG, US, and E are equal to the difference of what it is currently subtracted by what it was previously. As you can see, it's positive Y now to compare the Y position versus time. However, I changed positive Y to positive X to compare the X position versus time. Here's the graph that compares the observed and the predicted model. As mentioned earlier, the X position was pretty accurate. However, the Y position versus time, though having the same period, had different amplitudes. As you can see, the initial amplitude was similar to the observed model's amplitude, but it began to decrease slightly. The reason could be because of dissipative forces such as air resistance, which results in energy going into another form such as thermal energy. To answer the first "what does it mean" question, we look at the energy graph. The energy principle states that if there is no energy transfer, then delta E, which equals to the sum of the change in kinetic energy, potential energy due to gravity, and potential energy due to the spring, would be 0. Since we assume no energy transfer in our model, and as you can see on the energy graphs, the total energy is constantly 0, the energy principle is therefore satisfied. To answer the second "what does it mean" question, we first calculate the period using the X position versus time. Like the Y position versus time, we find the time when it reaches the first trough and the time it reaches the fourth trough and take the difference and divide by 3. Using this period, I calculate the stiffness of the spring as shown and get 5.855 newtons per meter. Using this K value, we compare the X position versus time and the y position versus time. And we see there's a greater difference here than it was previously. Both the period of the x position and y position versus time should theoretically not be different since their periods are dependent on the stiffness of the spring, which should be the exact same. So the reason for this difference could be due to dissipative forces mentioned earlier. In this lab, we were able to model an oscillating spring, learn about potential energy due to the spring, apply the energy principle, and calculate stiffness of the spring from the period. Thank you for listening.